first lecture in the advanced aircraft control system. Uh, Here we are not going to talk much on the contents or the references what you're going to consider for this course. This is already discussed in the outside. So in today's lecture, we'll be discussing why this we need to design the control in the state space domain. And what is the motivation, why it is important for aircraft system. So we'll go through the details. And also we have the motivational example, how the transfer function based control and the state space based control are very important, and which is better and which is not good for the multi-input and multi-output systems. So let's start with the course. So here we're going to study the control system as I mentioned. So let's assume we have some system, which is some scalar system. Let's assume some scalar system, which is x dot equal to x plus bu, and which is controlled by a control input, which is u, and the output of the system is defined by y. So this is the plant. We can say this is the plant, and this is, we can say, y equal to x. So this is the, you can say, scalar system and scalar input, and this is the output. And if you notice in the system is controlled by the scalar input u. Whatever the input is defined, and based on the input, the system will respond, will get the output. So there is no ways to control the control input u. Whatever, based on the predefined signal of u, the system will respond. Now, if you translate this system into closed loop form, where we can make the system automated. So we need to design, in this case, the U should be defined, predefined, but we can design some kind of closed loop control system where U can be generated automatically, which helps the system output to track the desired reference signal. So let's assume we have the controller here, and this controller is giving the control input, which is u of t, and this control input is going to the plant, which is x dot equal to x plus bu, and the plant output, which is given by y of equal to x. This is the plant, this is the controller, and this controller takes the error signal that is coming from the summing point. In summing point, we get the difference between the reference signal of x, and also it gets the feedback signal from sensor, which is, we can let's denote as y of t. And this is the sensor. For example, we have the sensor on board the aircraft or on board the plant. Is the sensor, and the sensor senses the current value of the system output. Okay. So here our main aim is, basically this is the closed loop control system, I can say, closed loop control system. And this is, we can say, this is the figure of a loop control system. So here we can, from this block diagram, we can write u of t equal to x reference minus y. So here, as we have to design u of t in such a that e of t goes to 0 as t tends to infinity. So in this condition, if e of t goes to 0, we can say our x reference minus y goes to 0. So in this case, we can say y going to track x reference. So this is how we can design the controller u of t through which we can track the desired signal. So this is the main purpose of the control system. This is the scalar system and how we can design the closed loop control system for a particular system here is what we have defined here. We can do. Now, if we would like to extend this concept for the aircraft application, so let's assume this is our aircraft. This is the aircraft. And we have these are the control surfaces. So here we can say this is we can deflect to the desired angle and show that the control signal can be provided to control the motion of the aircraft. So, and also we have the engine which provides the desired thrust to the system. So let's assume the force we are getting delta T, and this is the control delta A, and this is the control which is going to control the surface delta E elevator and delta R. So these are the control signal going to deflect the control surfaces so that we can get the desired signal to propagate the aircraft dynamics. So if you notice here, to maintain the orientation and position of this aircraft, we need to apply different controls to the different surfaces and also to the engine. So for this, let's assume the control input for this aircraft system. Let's write in vector form delta E elevator, delta R radar, delta A aileron, and delta thrust. So this is the control input that can be given by the controller. And this controller input going to the system. Our system is, this is the system. This is nothing but for this purpose, it's aircraft. So this is basically, we can say, six-stop equation of motion. So this is already we have done our first course. And from this, we can get the desired output from this aircraft system, which can be your X, Y, Z position of the aircraft, and also the angle of the aircraft, which is phi, theta, and psi. So our aim is we're going to provide the control inputs, which is the U signal, which is going to the servo system, and servo system going to provide desired force and torque to the dynamics of the aircraft, and the dynamics of the aircraft can be propagated so that we can get the desired position and angle of the, we can maintain the desired rotation angle of the aircraft. Now the question is, how we're gonna measure this signal? Because these are the current position and angle of the aircraft. How are we gonna measure this signal? So here we should have some navigation system This is, you can say, navigation. Also, you can say sensor and navigation system, which senses the two states of these values. This can be installed on the onboard the aircraft or maybe on the ground, which senses the current position and altitude of the aircraft. And through some estimation technique, we can use some kind of navigation filter, and we can get the estimated values of the states. We can say this is estimated states. So if you notice in this flow diagram, we have going to have multiple control input at a time, which is going to control multiple states of the system, and all the states can be sensed by sensors, onboard sensors. So in this case, it can be accelerometer, gyro, or any other sensors or GPS system, whatever sensor we install in the aircraft. Those sensors will sense the current attitude and position of the aircraft. Right. So now, if you put them all together in closed loop fashion, what you have done in the for this particular scenario, for this case, so here also you can do the same thing for this particular case as well. So let's now draw a figure where we can see how the different subsystems in the aircraft are connected in closed loop fashion. So we have let's start with the reference signal. The reference signal here, we are going to control different state, position as well as the angle. So X reference, nothing but a vector. So here X, Y, Z, phi, theta, psi. These are my reference signal. Here, let it down a little bit here. These are my reference signal. And this reference signal, I can use different. So this reference signal, I'm going to the summing point where we can do the reference signal. We're going to our next part is controller. So controller is we can the controller. Is the controller, and controller gives the desired signal, which is going to the servo system on board the aircraft. You can say this is the servo system, and this servo system provides the desired forces. I can say torque and forces, which is going to the aircraft dynamics. Aircraft dynamics. And this provides the actual values of the X, Y, Z of the aircraft position as well, phi, theta, and psi. So we can have a navigation system on board the aircraft, and we have the headlight. This is plus. So I can share this is the navigation block. So it's find the estimated values of the state. So this is the sensor also can put here. So this is how the aircraft control system works. So here, if you notice here carefully, we can control multiple states at a time. There actually you can say this is basically in vector form. So we can send multiple control input so that multiple states of the aircraft can be controlled. But if you look back over in the previous course in the transfer function-based control, where we have designed the control algorithm which can control one state at a time. Basically, the controller basically handles the CISO system, single input and single out. So here actually we can control multiple states at a time. So that's why state space based control design is quite important for the aircraft application. Once the aircraft system become so complicated and nonlinear and coupled. In that case, the system is the state space based control system is very important for designing multiple states to be controlled. So now this is how the closed loop control system works for the aircraft. Now let's look some concept in control. What are the different how the control system connected in real application? What are the different subsystems are involved? So this is only for control, but here also we have the navigation part as well. But in this course, we are not going to discuss much on navigation. Here, mostly we'll be handling control, how to design the control algorithm so that the system can follow the desired signal over time. So typically the control system, we are having different subsystem. So let's go step by step. So here, as we have done in the previous phase, that in the control system, we should have the navigation block, which provide the estimated values of the system. And these estimated values goes to the guidance system, and guidance system find the error between the desired values and actual values. So desired means the reference signal. So guidance system basically find the error between the desired values and actual values, and this command goes to the controller. So guidance system provide the error signal which is going to the controller, and controller tries to correct it. This is going to the controller. And this controller generates, and the controller U goes to the actuators. So here actuator is nothing but the aileron, radar, and elevator. We can write aileron, radar, elevator, and engine, we can say. So this provides the force and torque, and this goes to the aircraft dynamics, and this aircraft dynamics provides the true signal. Basically, this is the actual position and orientation of the aircraft, and this is equals to the sensor part, and this sensor goes to the sensor values goes to the navigation, so that some estimation can be done in the navigation system. So this is how the typical aircraft control system works practically. So here we are having different subsystems which has the own merits to design the control objective fulfilled. So this is how the modern control is very important practically, and where we can control multiple states at a time. But in the classical control, it is fully transfer function based control. So we can control one state at a time, but in the modern control, we can control multiple states at a time. So which is very desirable for such complicated aircraft system. So now, how we can find for particular system a state space model and transfer function model, because this is also important. Some example, let's take. So how we can convert a system where we can convert into state space model and also transfer function. So let's assume we have simple mass spin damper system, nx double dot plus dx dot plus kx equal to u of t. So I'm not going to detail of it. This simple second order system, which can be derived from the simple mass spin damper system. So here, from this system, we can write two different form of equation. One form of equation in transfer function form, and one form also you can write in state space form. So if you would like to write in state space form basically defines the system into first order ODE. So if you notice, this equation is the second order system. So we have to convert into first order differential equations. So in that case, we need to apply the change of variables. So here we can write x1 equal to x and x dot equal to x2. So I can write x1 dot equal to x2, and x2 dot we can write minus p upon m x2 minus k upon m x1 plus u of t. So these two equations we can find from the given equation. So this equation can be found from this. So in the transfer function form, okay, let me work on this more. So if you notice, this is basically two first order ODE, two equations. So if you write in state space form, we can write. So there are two states here. One is position and one is velocity. So we can write x1 dot, x2 dot. We can write the matrix form 0, 1 minus k by n and minus b by n into x1, x2 plus 0, 1 into u of t. But in this system, only one control is there, single control input. So here, if you notice in this equation, so two states can be controlled, multiple states. But if you write in transfer function form, one thing, as you have done in the previous course, that to find the transfer function of the system, we need to consider the initial condition to be 0. Because if you consider non-zero initial condition, the superposition principle cannot be validated. So, and system will be nonlinear. So, to find the transfer function, we need to consider the initial condition to be 0. So here, if you consider for 0 initial conditions, if we apply the Laplace transform for this equation, we can get m s squared x of s plus bs x of s plus k x of s equal to u of s. Or we can write x of s divided by u of s equal to 1 upon m s square plus bs plus k. So this is the transfer function for this mass spin dipole system. And this is the state space form of the same system, mass spin dipole system. So this is how we can study the classical control techniques and state space based control techniques. In state space based, we have to convert the system to defined form so that we can design the controller in such a way that multiple states can be controlled. But in the uh, transfer function based, basically, if you notice here, it is actually seesaw form, single input and single output. But here we can say multiple input, multiple output. But in this case, anyway, the single input. But we'll have more examples where we can have multiple input as well. So this is how we can study in modern control, how we can control multiple states of the system using the state space based control synthesis. Let's stop it here. We'll continue in the next lecture how we can come up the all more on the how we can design the different control parameters in the system and how we can look in more detail to push it further on this course. Thank you.